This is a lecture about the hydraulic architecture of trees and how the structure of tree xylem, the water conducting cells in the stem of the tree, influences not only water transport but also the regulation of water transport by trees in response to the environment. So I'm going to start by I'll just put up front as sort of a trick question. Let's imagine that you have a beaker. So we have a beaker here that has water in it. Okay, so there's water in it. And let's say we want to drain this beaker. So we're going to put a pipe or a number of pipes on the bottom of the beaker to drain it. And we have a choice of these three sets of pipes. We have that big pipe over here, or we have a series of 16 pipes here, or a series of a whole bunch of pipes here. If one of those three arrangements was on the bottom of the beaker, which one would drain fastest? And of course, because you know this is a trick question, the answer is it would be the same. So that's because the hydraulic conductivity, the ability of either that single pipe in the top left or those 16 pipes there or that large number of pipes there, given the same pressure difference as you would have on the bottom of that beaker, they have equal ability to transport water. The relationship that governs that is the Haagenplaceal relationship. And this is just an engineering relationship which expresses the amount of volume of a liquid per unit time that can move through a pipe of radius r. Okay, so this is the radius of the pipe at a given change in pressure. So that's pressure per unit length of the pipe. And then you've got pi here, and you've got a constant here, the Haagenplaceal constant. So what that shows us is that the radius of the pipe is hugely important because it's raised to the fourth power. What that tells us is if you have a pipe with a given pressure difference across it, and you increase the radius of the pipe a little bit, that very greatly increases your ability to transport volume of water per unit time. Because a little increase in the radius of the pipe, its effect in terms of water transport is raised to the fourth power. So that tells us that the radius of a pipe has a huge influence on its conductivity, its ability to transport water. So we can think about the effect of the radius of a pipe on the biology or the structure of different types of xylem. So we've got, conifer xylem here on the left with its tracheids, and we know that tracheids have relatively small diameter versus this is an angiosperm xylem here on the left. It's a diffuse porous angiosperm. I believe this is a maple. And if you look at, for instance, the size of those maple vessel elements versus these conifer tracheids, it's a big difference. Okay, and that sort of plays out in what you see there. There are many, many conifer tracheids and much fewer angiosperm vessel elements. That's because those angiosperm vessel elements are larger in diameter. We talked way back when we talked about structure about the evolution of vessel elements as essentially an evolution from tracheids, which perform both mechanical support and water transport functions to vessel elements which perform water transport function, and the separation of mechanical support function into fibers, which provide mechanical support. And one of the benefits of that, one of the adaptive benefits that evolutionary change entailed was that vessel elements are much more efficient at transporting water. So the separation of that water transport function to vessel elements and mechanical transport to fibers, that was essentially in enabling the growth of bigger vessel elements that provided more efficient water transport. Now, this differing ability of particular xylem structures to transport water can be quantified using hydraulic conductivity or hydraulic conductance. So that should sound familiar to you because it is structured similarly to, for instance, stomatal conductance. You could also think of it as a resistance. You could have a hydraulic resistance, which just refers to the resistance to water flow through xylem, and I have referred to that before. So I'll, as usual, I'll be flipping back and forth between resistance and conductance, and again, those are just inverses of each other. But in this case, we're talking about liquid water rather than gaseous water, as we were when we talked about stomatal resistance or stomatal conductance. But they are similarly derived from an Ohm's law analogy, where that Ohm's law says that a flux is equal to a potential difference divided by a resistance. So we can translate that into the flow of liquid water through a tree, where the water flow through a tree is related to a water potential gradient, for instance, from the roots of the tree to the leaves, or through any segment, maybe just a branch, from the start of a branch to the end of a branch. Regardless, that's the water potential gradient. It's just the water potential difference across that segment of xylem divided by hydraulic resistance. Okay, so we can solve for hydraulic resistance. So hydraulic resistance is just the water potential gradient across a segment of xylem divided by the water flow rate at that water potential gradient. Now, again, in most modern physiology, we talk about conductances instead of resistances. So what you generally see in the literature is a conductance, a hydraulic conductance, often expressed as KH. So that just means hydraulic conductance. And that would be a water flux, the amount of water flowing through a segment of xylem, divided by the water potential difference across that segment of xylem, divided by the length of that segment. So it's normalized per unit length of whatever segment you're measuring. So, for instance, if we have a pipe or a segment of xylem, and we know there's a water potential at one end, or a pressure at one end, and a water potential or a pressure at the other end, that's that water potential difference. And then we know there's some length here. That allows us to normalize that pressure difference. And the amount of water that flows through that segment at that water potential difference would give us the water flux. And then that would allow us to plug everything into the right-hand side of that equation and derive a hydraulic conductance. That's basically exactly how we measure hydraulic conductance of segments of xylem. we basically will push water through a segment of xylem at a known pressure and measure the amount of water that flows out of the end. And that gives us everything on the right-hand side, and then we can calculate a conductance for that particular piece of xylem. So clearly, given, for instance, the same pressure difference, a xylem segment with a greater hydraulic conductivity will be able to move more water. Okay, so it takes another way to think about it is it takes a larger water potential difference to move the same amount of water through a stem with a lower KH, or a lower hydraulic conductivity. So hydraulic conductivity allows us to think about the relationships between water potential gradients and the amount of water that can flow through a particular segment of xylem, for instance. And another calculation that you often see in the literature is Leafspecific hydraulic conductivity. And that just equals KH divided by leaf area of that segment being measured. So for instance, let's say we have, a branch with leaves on it. And we've measured hydraulic conductivity through that branch. We can calculate KH as we described earlier from this, but then we measure the leaf area of that particular branch and normalize that KH value by the leaf area on that branch. You can do the same thing for an entire tree if you had the appropriate measurements, for instance. So that leaf-specific hydraulic conductivity is a pretty common formulation as well. We can look at species variation in hydraulic traits. This table shows for a number of different life forms their sort of typical variation in hydraulic resistance. So again, we're talking about resistance in this particular table, just the inverse of hydraulic conductance. So a smaller number for hydraulic resistance just means a greater ability to transport water. Larger value obviously means greater resistance to water transport. So these are sort of arranged from high resistance to low resistance. And what you can see sort of ranges from, gymnosperms to diffuse porous angiosperms to ring porous angiosperms to herbs to lianas. Okay. They also show maximum sap velocity. So as you go to life forms with less resistance, you get a lot faster sap transport. And if you look at sort of typical conduit diameter, and when I use the term conduit diameter, that conduit is just a generic term for vessel element or tracheid. It's just a faster way to say that, because obviously in different life forms, some life forms don't have vessel elements, some life forms only have tracheids, but conduit just means pipe. So it's a different way to express that. So obviously we go from small conduits or pipes to large. So, evergreen gymnosperms just have tracheids, so their pipes are quite small. Diffuse porous angiosperms have sort of a medium number of medium-sized vessels, whereas ring porous angiosperms have a smaller number of very large vessels, and then lianas tend to have enormous vessels. Think about why lianas are sort of on one end of this scale. Why do they tend, or why are they able to produce enormous vessels? Well, it's because they really don't need much mechanical support, right? Lianas are vines that hang on other organisms like trees. So they have very few fibers in their stems. So their stems, the vine, is almost all vessels. And those vessels can be very large. So lianas just have enormous vessels and very low resistance to water flux. They're at one end of the range of this variation. Let's look at this in another context using the heuristic equation that we've used in previous lectures, where water potential of a leaf, for instance, is proportional to soil water potential minus transpiration rate times hydraulic resistance. Okay, this should look familiar because we talked about it in a previous lecture. But remember, previously we really didn't talk about this term, but obviously that's the topic that we're talking about here. So let's think about that relationship given this graph. And in this graph, the scientists measured water potential of leaves of 3 different species of trees. So the different symbols of the different species of tree. And they measure them throughout the day. So basically they went up into the crowns of these trees, measured the transpiration rate of the leaf, and then plucked the leaf off and measured its water potential at that point in time. And did that at several points throughout the day over a diurnal period, and then plotted them. So this is transpiration rate. Okay, so that's that term. TFD is just transpirational flux density. So that's transpiration rate. And then this is the y-axis is water potential measured at those different times a day. Okay, so first let's look at any individual line. What we can see is the pattern that we would predict and that we've already talked about in previous lectures, where an increase in transpiration rate, all other things being equal, results in a more negative leaf water potential. Because as the transpiration rate gets larger, that increases that right-hand term, and leaf water potential will become more negative. So you can see that that's happening. So for instance, for this leaf, as transpiration rate increases, its water potential is becoming more negative. Okay, so that makes sense. But what you can see is that for a different species, in this case this is white oak here, it also declines, or its water potential becomes more negative as transpiration rate increases, but it happens at a steeper slope. And then this one, which is eastern red cedar, it has a very steep slope. So they all see a decline in leaf water potential as transpiration rate increases, but they decrease at different rates. What's causing that difference? Well, it should be obvious that the difference in the rate of decrease has to do with different values of hydraulic resistance. The greater the hydraulic resistance, the larger this term is, the more steep this decrease is. Okay, so the eastern red cedar has a higher hydraulic resistance. And in this case, the black walnut has a lower hydraulic resistance. Okay. Well, what about the soil water potential in the equation? Well, remember, pre-dawn water potential when transpiration rate is 0 essentially is a measure of soil water potential. So basically, those zero transpiration water potentials, that's a measure of soil water potential. So that is basically size soil here. And then the reduction below, or more negative than soil water potential, that happens as transpiration happens, goes from there. Okay, so this graph sort of ties all those terms together, and we can see how variation in hydraulic resistance then influences how an increase in transpiration will generate a change in water potential, and that change in water potential, the degree to which water potential changes, will vary depending on whether that plant has a high hydraulic resistance or a low hydraulic resistance. And we can also see how those hydraulic resistances are related to the xylem structure. Eastern red cedar is a gymnosperm. It has tracheids and very small conduits. Okay. Now here, the white oak is a ring porous species, which actually has very large conduits, and the black walnut is a diffuse porous species. I actually might have guessed that the ring porous oak might have a lower hydraulic resistance than the diffuse porous species, but as it turns out, basically the greater number of medium-sized vessels in the diffuse porous black walnut basically resulted in a lower hydraulic resistance than the smaller number of larger vessels in the ring porous species. At any rate, I really love this graph because it ties all of the terms in that equation together, and we can see how they all interact to influence the development of water potential gradients in species with different hydraulic resistances. This graph shows some hydraulic conductivity data collected by Frank Ewers and Martin Zimmerman. Martin Zimmerman was a biologist at Harvard University who's sort of one of the founding parents of xylem hydraulics. Zimmerman wrote a book called Xylem Structure and the Ascent of Sap that was later released in an updated version as Tyree and Zimmerman. So I really encourage you to check that book out of the library and read it. It's a great pioneering work that really helped me understand the concepts of water potential and xylem hydraulics. At any rate, what Ewers and Zimmerman did was they took a balsam fir tree and took it apart and then measured hydraulic conductivity in segments of xylem in the way that I described to you, where they took a segment of trunk or branch and forced water through it under pressure, so they know the pressure on the pressurized end, the pressure on the open end, and the length of the segment. And then they measured how much water came out under that pressure gradient. And in this case, they normalized it by the leaf area downstream from that segment of xylem. So these are leaf-specific hydraulic conductivities, as we've described earlier. So the left tree there is leaf-specific hydraulic conductivity of different segments. And what you can see is a couple of things. One is that the highest leaf-specific conductivity are in the main stem. And that you see smaller leaf-specific conductivity in smaller branches. And Ewers and Zimmerman hypothesized that what this did was essentially create zones of lower hydraulic conductivity out on branches. And they hypothesized that this created sort of hydraulic restrictions in the crown where, for instance, way out here, where leaf-specific hydraulic conductivity was really low, that is where the greatest drop in water potential would occur in this hydraulic system. So you can see those really small hydraulic conductivities happened out here, so that in water transport, you'd see the biggest drop in water potential way out there on the branch tips. Now, later on, we'll talk about how reduced water potential causes cavitation, breakages in the water column. We'll go into that in detail later. But basically what they hypothesized was that those very low conductivities basically moved potential breakages in the water column out to the ends of the branches and made those sort of vulnerability to cavitations happen at the very ends, so that breakage of the water column happened at the ends. And so that if you lost segments of the xylem, it happened on external branches and not here in the main stem. So basically the tree can afford to lose little branches out at the end, but the tree can't afford to lose the main stem. So they hypothesized that part of the evolution of these lowered hydraulic conductivities was to sort of make those hydraulic constrictions out at to basically make the more vulnerable parts of the crown be the parts of the crown that could afford to be lost. I sort of stuttered around that, but essentially that was core to their hypothesis. So they almost thought of those hydraulic restrictions as safety valves that concentrated cavitations in branches and leaves and keeping those cavitations away from the main stem of the tree.